I return to the microphone to introduce the next speaker, Christophe Fraser from Imperial College.
Thank you. Okay, so I'm going to talk about trying to predict the evolution of resistance. And to predict the evolution of resistance, we need to measure the fitness cost of antibiotic resistance. So the principles of selection have been understood for over 200 years. And in this case, the idea is that if you consume more antibiotic, you will select for things which are more resistant to it. That story is simple. Unfortunately, it's not quite true. And the temptation is to say that antibiotic resistance is old and complicated, and just to shrug and say it's complicated. But I'm, unlike antibiotic resistance, I'm still quite young and still quite simple. And I'm determined to sort of, I think, we shouldn't give up. We saw in Nick Crouch's talk illustrated beautifully the complexity of antibiotic resistance. There's a veritable zoo of antibiotic resistance genes which have been around for millions of years. A couple of weeks ago, there was a report of finding them, a mile under the ground. Antibiotics, there's a huge diversity of antibiotics. So there's a huge diversity of antibiotics and a huge diversity of antibiotic resistance genes. And you would be entitled to just shrug and say, well, it's complicated. But just bear with me for the sake of these 20 minutes, at least. So why does the cost of resistance matter? Well, resistance is an evolutionary process. Fitness is the key quantity which determines evolution. And fitness has proven hard to measure. So how is it typically measured? Well, it's measured typically by competing different strains against each other within well-defined environments. The difficulty is finding the correct environment or the representative environment within which to compete them against each other. So you can compete them against each other in vitro, in a mouse, in a rabbit. And the problem is that the results tend to be dependent on the context, and they also tend to be hard to replicate. So you find that sometimes one strain wins, sometimes another does. So here the idea is to reverse engineer the problem and to try and instead estimate the fitness costs that would have been necessary in order to explain what has happened at the epidemic level. So essentially, we're going to try and fit a mathematical model to the data. And we're going to take advantage of a natural experiment. And the natural experiment is basically doing a sort of ecological comparison between different strains adapted to different niches. And probably the most important thing to look at in terms of differentiating different strains of the pneumococcus is the capsule, which is classified into different capsular serotypes. And the serotypes are very different from each other. And here I've taken some pretty pictures, and I've made them green because in order to avoid getting lost in the sort of alphabet and number bingo of different serotypes, I thought it useful to give them different personalities, and they really are different. So here we've got the purple one, who's got a nice regular haircut, and this one is not frequently found in carriage, and if it is found in carriage, it tends to be cleared very quickly. 19F is at the other end of the spectrum. It's got a very tight, shorter haircut. And this one, when it gets into carriage, tends to be carried for a longer period of time. And the idea basically is to look for differences in resistance and patterns of resistance in these different serotypes. And the idea is that basically these ones which are carried for a long time, so the 19F type ones, which are carried for a long time, have more to lose. So if you imagine antibiotic consumption as being an ongoing process where parents of kids say, I want antibiotic for my kid, and the antibiotic is given because the clinician's scared. Another story, which we'll hear about tomorrow, I'm sure. This one has already sort of been in, done its business, and gone, whereas this one has a tendency to stick around a long time. Therefore, it has more to lose out of over-prescription of antibiotics. And the prediction is that the 19F type ones, which are carried for a long time, should be resistant. So we're going to check that. Now, in order to find these pictures, obviously, as a theoretician, I didn't go anywhere near an electron microscope. I just searched Google Images. And it's kind of interesting that if you do search for Google Images for Pneumococcus capsule, you find a whole bunch of pictures, of which I think I chose the prettiest, but not quite the prettiest, because in the middle of all of the capsules, you find this picture here. And actually, it's quite apposite, because the sort of genesis for this comparison was through collaborations with Mark, and Mark has actually determined at a molecular level and in vitro and in epidemic sort of correlated why these different serotypes have different amounts of success. So now I'm going to say the same thing. I'm going to say the same thing using maths. So this is an equation. So this is the rate of change of the number of sensitive bacteria. This is the rate of change of the number of resistant bacteria. And the sensitive bacteria get cleared more quickly because of antibiotic consumption, and the resistant ones obviously are resistant to antibiotics, so they only get cleared through the natural process. But they're also a little bit less fit, potentially. This is what we're going to try and estimate because of the fitness cost. And out of that model, we can make a simple prediction, which is that there's competitive exclusion. So if antibiotic consumption is high enough, then basically you're going to select for resistance. Resistance is going to grow exponentially, then it's going to saturate the population, and it's going to go to fixation. And how much antibiotic consumption you need in order to provoke this selection of resistance depends on the fitness cost. This equation is well known, but in the context here, the novelty is actually the bit which is often ignored, is this alpha term here, which is a natural clearance rate. And here we're going to look at the fact that this actually varies by serotypes, and it varies quite substantially. So our prediction is that serotypes of a high natural clearance rate, i.e. a short duration of carriage, are unlikely to be resistant. So here's some data collected by Mark Lipsitch and Osman Abdullahi in Anthony Scott's group in Kilifi in Kenya. And actually these, we were looking at this, we use these data because they have the highest resolution, but they actually do seem to match quite well with previously published estimates. And here's your 19F1, which is one of the more common one, the green tight head one. So he tends to be carried for a long time, so he's got a low, he or she's got a low clearance rate, and we expect them to be more resistant. And here's a serotype 1, lots of uncertainty here, but we're pretty sure that he's not carried for very long, and he's less likely to be resistant. Then to look at whether this prediction comes true, we looked at the data from, collected from Matt Moore's group at the Center for Disease Control, the active bacterial core surveillance. There are approximately 3,500 clinical isolates, so pneumonia, bacteremia, meningitis, collected annually from 1996 to 2007. Because of the effect of vaccine selection, we didn't want to look at vaccine selection. We looked at 1996 and 1997. The isolates are serotyped, and they're tested for resistance to penicillin, erythromycin, tetracycline, cotrimoxazole. They're also tested for a few others, but I'm going to ignore them because they're fairly rare. The MICs are determined, but I'm going to use a simple-minded susceptible resistant classification for now, because that will be complicated enough. So with that classification, stratified by serotype, each of these bar charts shows you for one serotype the proportion of isolates of that serotype which are fully sensitive, resistant to at least one of those antibiotics I mentioned, 2 of the antibiotics, 3 of the antibiotics, or all 4 of the antibiotics. And here at the bottom are the long carriage ones that were predicted to have lots of resistance, and here are the short carriage ones which are predicted to not have very much resistance. And you should be able to convince yourself without much statistical analysis that the prediction does indeed come true, that there is far more resistance and multi-drug resistance here on the bottom row than there is on the top row. Here's the 19F chart, and here's the serotype 1 chart. Serotype 1 is almost always sensitive. But the other ones which are like it are also almost always sensitive. So that does seem to verify the prediction. So there does seem to be an organizing principle. We can plot this, for example, different summary statistics. So here's proportion of isolates that have any kind of resistance and the clearance rate, and you have a correlation which is highly significant and explains about 20% of the variation. That correlation is not brilliant, but we have lots of uncertainty in all of the parameters, so we'll do. Here's 19F up here, serotype 1 down there. Obviously, fitting a straight line may not be the best thing, and it also points to a particular problem. If you remember, the model I sort of used to justify this thing actually had competitive exclusion. So it predicted that the serotypes should either be right at the top here, fully resistant, or at the bottom here, fully sensitive. And actually, these serotypes here have been resistant, and they've been resistant in this middle level for 20 years, and they haven't been changing, even the introduction of the vaccine. I mean, they bob up and down, but there's no systematic trend. So there's a puzzle there, and it needs to be explained. And with Caroline Colline and Mark and Ted Cohen and Bill, all of whom are here, we racked our heads a few years ago, and we wrote down all of the, we wrote down a whole bunch of models. We wrote down many more models than these, but here are the ones that made it to the paper, which tried to explain this coexistence in terms of sort of a mechanistic understanding, the heterogeneity in the contact process, and so on. But a while ago, it actually turned out that we found a different model, which is maybe slightly less, well, is less mechanistic, but is a very easy way to explain, to generate coexistence and to get rid of competitive exclusion. And it's simply to introduce a power above the number of infected people here. And if that power is exactly 1, you have competitive exclusion. But the point gamma equals 1 is actually a bit of a special point. In maths, it's a critical point. And it separates the regime where gamma is less than 1, where you have coexistence between different types, and gamma equals greater than 1, where you actually have multiple equilibria, so where the initial conditions matter, and you essentially get survival of the most common rather than survival of the fittest. Now, this can seem like a bit of a fudge, but on the other hand, if you've gone through the process of how the mathematical models of transmission were formulated in the first place, the choice of gamma equals 1 is also a bit of a fudge. So this is a little bit of a fudge, but the basic models, which is changing, were also a bit of a fudge. Because if you go back to the definition, essentially it says, let's begin by assuming that people are mixing like a perfect gas. Now, I don't know about you, but I certainly don't mix as we don't mix as perfect gases. And even as it turns out, gases themselves don't mix as perfect gases. So if the epidemiologists who'd founded those first models went to page 2 of their sort of chemistry of gases, they would have found the model with this gamma term on it, and we may not have regarded that term as so unusual. So what does that gamma term do to coexistence? It actually does quite dramatic things. As I said, gamma equals 1 is a critical point, and therefore just changing it even to 0.99 changes the dynamics dramatically. And once you get to gamma equals 0.9, the dynamics are completely different. So here I'm showing for a given fitness cost and given natural clearance rate, the effect of varying antibiotic consumption. And you can see that when gamma equals 1, so the standard model predicts competitive exclusion, so it's either frequency of resistance is either 0 or 100%, but if gamma is 0.99, there's a whole regime, whole parameter range, where the sensitive and resistance can coexist. Anyway, that's a little bit by the by. So the model we come up with is a multi-strain model that has this gamma here, and essentially we have 2 to the 4, so 16 strains, ranging from the fully sensitive, 0.001 means sensitive to all drugs apart from resistant to cotrimoxazole. This one's resistant to tetracycline, and this one's resistant to all 4 drugs. So we have 16 strains, and we can put in an analytical solution. There is an analytical solution to this model, and we can fit this model to the data. So the bit which is missing data on drug consumption. So we need data on drug consumption. So Herman Gussen's group has specialized in documenting drug consumption in Europe, but in a couple of papers, he's also documented it in the United States. It's defined in defined daily doses per person per day. And altogether, it's something like 2.5% of Americans are on antibiotic on any given day. And this is how they're distributed amongst the different drug classes. The main problem is we don't really know how defined daily doses prescribed translate to actual clearance rates, so we have one arbitrary parameter here, k, which now, for the sake of argument, I'm going to fix to 0.1. But that's something that we need to explore further in further work. So the fitness cost of resistance. We have all of the ingredients. We have the resistance data, we have the natural duration data, and we have a model, and we have consumption data, and we put all of that together, and we put it into a big inference framework, and sort of whirs away. And if you're not a theoretician, and you wonder what theoreticians, sometimes people who work in labs, they wonder what it is exactly theoreticians do all day, where we sit around and we wait for the answer to come out. And when the answer comes out, we look at it and we think, wow. So for those of you who haven't read or heard or seen The Hitchhiker's Guide to the Galaxy, this is the answer to the meaning of life and the biggest question in the universe. And it was based on constructing a computer to answer that question, and ran for thousands of years and eventually produced the answer 42. As it turned out, the fitness cost of resistance was also 42 until we realized we'd made a bug in the code and rerun it. So this is the latest estimate, and I will say these are preliminary results, so we need to, and they're fairly hot off the press, a couple of hours old at least. So what I'll tell you is that if you're really interested to know the final number, wait till this paper comes out. Hopefully it shall do fairly soon. So I'm not completely confident that all of these points won't drift up a bit or drift down a bit. What I am fairly confident about, because we've now fitted it enough times, is that this general pattern is really robust. It's a general pattern which is robust. And the two things about the pattern which are notable is, first of all, we didn't actually have an expectation a priori why the fitness cost shouldn't just be 0, because we know if you evolve these things in the chemostat, there are compensatory mutations. On the other hand, these resistance genes are quite complicated and they're diverse, and maybe the adaptation time and relaxation time of the system is completely unclear. But consistently, we find a double-digit fitness cost. The second thing that we find consistently is we find pretty heavy fitness cost for individual drugs. Cotrimoxazole, the less costly, and tetracycline, the most costly, so the ordering tends to be very consistent. And double resistant then becomes a bit more costly, but then the funny thing is it really flattens off. So fourfold drug resistant is actually not that much more costly, or doesn't come out as being that much more costly to the pathogen as single drug resistant. And that's a really robust finding of this particular way of analyzing the data. And the way that's described is in the language of interaction between genes, and the language is epistasis, and this is actually positive epistasis and occasionally sign epistasis. So positive epistasis is when the fitness cost is somewhat less than we would have expected by comparing them as independent entities, and sign epistasis is when they're actually acting. So, for example, cotrimoxazole seems to act as a compensatory mechanism to other types of resistance. So having twofold resistance actually improves the fitness of the strain rather than reduces it. So here's sort of showing it in numbers. These are the estimated costs for the 4 individual drugs. And for the 4-drug resistance, the cost comes out as only 14%, whereas the expectation, assuming independence, would have been 22%. Now, that's a fairly sort of surprising conclusion. It helps explain multi-drug resistance. And a slight sort of maybe indication, there is a different bug and different drugs and different mechanisms. But when people have looked at interaction between fitness costs of, in this case, E. coli, the fitness costs were estimated to be very similar from the ones we estimate from our epidemic modeling, and the interaction terms, positive and sign epistasis, was something that was also observed in this system. So, you know, if you like your findings to be grounded in sort of in vitro things rather than modeling, we do find this important trend which helps explain why pneumococci tend to be either fully sensitive or really quite multi-drug resistant, and is explained in terms of this interaction, which is definitely worthy of further investigation. And we've also determined which serotypes are more likely to be multi-drug resistant and why. It's those which have sort of more to lose because of a longer duration of carriage through their life history. In conclusions, different serotypes vary in their resistance because of their different clearance rates. That prediction does seem to be true. Long-duration serotypes have more to lose by antibiotic consumption and are more likely to be resistant. I won't yet put my neck out on the line to say what the fitness cost is, but it's probably at least 5% and probably a 2-digit fitness cost, which is quite surprising, and it definitely appears to be greater than 0 for all the drugs we looked at, all the drug resistances we looked at. And we found a consistent signature of negative and even sign epistasis, which is biologically unexpected, but does match up with what people have found in the competition experiments in vitro and helps explain multi-drug resistance. And to finish, I'd like to thank my collaborators, Caroline Colline, who was at Bristol and now at Imperial College, Sarah Deeney at Imperial, Matt Moore in the CDC ABCs program, Osman Abdullahi and Anthony Scott, and more locally here, Bill Hanage and Mark Lipsitch, and the Royal Society and the Medical Research Council for funding. Thank you.